Okay, so I'm going to get started talking about reactions of alkenes. So this is pretty exciting. This is our first big set of reactions that we have to deal with. So what we'll start talking about is just the basic reactions of alkenes. So what you should know is every type of hydrocarbon, every type of hydrocarbon derivative, everything we're going to talk about in this class, they all undergo combustion. And it's the same with any hydrocarbon derivative. The products are always CO2 and water. So that is just sort of the understood for any hydrocarbon. I probably won't take much time talking about those in future classes, future lectures, just because everything does it. We've already covered that. Now, like with any functional group we're going to talk about, the functional group is the site of the reaction. So no matter how big and gnarly the compound is, the reactions that it undergoes are going to happen at that functional group. So there could be this huge string of carbons, and it really doesn't matter because what we're going to focus on is what's happening at the double bond. That's what's going to happen. All this other stuff is just not part of the reaction. It's just going to hang on and show up at the end, but it's not really going to affect how the reaction happens. The type of reaction we're going to deal with is called an addition reaction. It's the only really important type of reaction we're going to talk about for alkenes and alkynes also in a little bit. So addition reaction, unlike a substitution reaction, which is what we talked about with alkanes, where we have carbon, H, and we remove a hydrogen and substitute it with something else, probably like a chlorine, some sort of halogen. What we're going to do is instead of replacing something or substituting something, we're going to just straight up add something. So this is called an addition reaction. Reaction in which atoms or groups of atoms are added to each carbon atom in a multiple bond in a hydrocarbon derivative. So what we're talking about is if we look at the double bond, we're going to be adding something to it. So what's going to happen is two new bonds will form, which breaks the bond before. So actually, let me show a little bit better of a before picture. So if you think about it, there's atoms over here. We don't really care what they are. I'm just drawing circles. What's going to happen is two new bonds are going to be forming, but if we didn't do something about the number of bonds it has, that's too many for each carbon. Notice that's 1, 2, 3, 4, 5. So what happens is this bond breaks, but not totally. Just the double bond breaks and forms two new bonds here with something else. So that's how we're adding something across the double bond. That's the basic mechanism of adding across a double bond. So erase this real quick. All right, moving on. So the general form of an alkane addition is we have the double bond. We're going to take something, and this A and B are just fill-ins for whatever compound we have. Now, A and B could be a single atom each, or A could represent a couple atoms. A and B, they could be the same thing. Or not. So A and B could be the same atom or group of atoms or not. So there's 4 types of addition reactions that we're actually going to talk about in this course. We're going to break it into 2 types. So we're going to have 2 types. There's addition reactions. We're going to break it into 2 subtypes. And one of them is going to be called symmetrical. Can't remember how to spell symmetrical. 2 M's, okay. And then unsymmetrical. I don't know why it's not called asymmetrical, but it's called unsymmetrical. And under here, we're going to have 2 types each. So we're going to learn 2 symmetrical and 2 unsymmetrical. So simply put, what symmetrical addition reaction means is A and B are the same thing. That's it. They're the same thing. We add the same thing to each carbon. Unsymmetrical addition reactions is where A and B are different. So 2 different things. Now again, I want to emphasize we're only adding things to the carbons that are involved in the double bond. We're not adding them to any of the other carbons in the compound. So there's two common types of symmetrical addition reactions. One is called hydrogenation. So an addition reaction in which H2 is incorporated into molecules. So in this type of reaction, where we had A and B before, if you look up here, A and B, just imagine that A and B are each hydrogen, because that's what a hydrogen molecule is. We simply are drawing it as H2, but it's really HH. And what's simply happening is one hydrogen's making a bond here, one hydrogen's making a bond here, and then we break the double bond. So we end up with this here. We're just adding something across. It's also important to note, you do need to know what conditions are necessary. So nickel or platinum and heat. This is actually the reaction that's happening in a catalytic converter in your car, converting exhaust, trying to take it from being alkenes to alkanes, which are a little more inert. So this is for the unreacted fuel usually. And that's why there's platinum in there. That's what that's for. And so heat and pressure are necessary also. So here we go. Hydrogenation of vegetable oils is an important commercial process. Now, we'll actually talk about the hydrogenation of vegetable oils way down the road in Chapter 19. So sort of just put that in your back pocket for the moment, and we'll get to that a little bit later. Halogenation is the other one. It's the same idea, right? Actually, I don't know why I'm drawing this. I bet I have an illustration here. Except for we have X2. So X2 could be Cl2 or Br2 or I2 or whatever. So we're adding halogens across the double bond. Simple. Now, this doesn't actually require any reaction conditions. It happens very readily. It happens very easily. Now, so chlorination and bromination are most often. No catalyst is needed. So there we go. Bromination is often used to test for double bonds in organic substances. We'll actually use this in the lab. And the way it works is bromine is, when bromine is dissolved in water, you get this sort of brownish color. So what happens is if you add bromine to a small amount of bromine to something with a double bond, to an alkene, what will happen is the bromine will react and that brown color just goes away. So you don't see the brown from the water anymore. So the other two are unsymmetrical. So I'm going to spend a little more time on the unsymmetrical reactions. There's two types of important unsymmetrical addition reactions. One of them is called hydrohalogenation. So with hydrohalogenation, all we're doing here is listing out what A and B are, what the two things are. Hydrogen and a halogen, so like HCl or HBr or HF or HI, any of these. And so what happens is we add, I'll show an example, double bond. We add, say, HCl, for example, and then we get H on one of the carbons and Cl on the other. Now, so you know, in this course, what I'll be asking you to do on a lot of exams and quizzes is I'll give you this first part and ask you to write the product. At times, though, you should know I may give you the product in one of the reactants and ask you to fill in the other reactant. So it can go either way. Hydration reaction is the other one. Now, hydration reaction is simply where this is a case where one of the two things being added is actually two atoms in one. So we have the double bond again, and I'm going to add water is what we're adding. So hydration is where we're adding water. We count one of the items as H and the other as OH. So one of these is going to get a hydrogen, and the other one's going to get an OH. And this actually makes what's called an alcohol, which is what we'll talk about next chapter in chapter 14. So we add water to the compound. So hydrohalogenation requires no catalyst. One carbon receives a hydrogen, one receives a chlorine. Hydrogenation, it requires a small amount of H2SO4, sulfuric acid. Water is added across the double bond. You get here, like this. So here is my H, and here's my OH. Now, we form an alcohol. Okay, so here there's one extra little rule we have to deal with unsymmetrical addition reactions, because the alkene itself might be unsymmetrical. So here's an example. Oops. So there's an example. It's exactly the same example I seem to have picked for my previous example. The two possibilities are where we get, except for I added HCl, I was thinking water. The possibility is that because the hydrogen has to go to one of the two carbons, and the chlorine has to go to the other one. So if the chlorine goes to the first carbon, we get this structure. And if it goes to the second carbon, we get this structure. So the difference is, and we can tell that these aren't the same. Remember, I always say you can tell if two molecules are the same or not by naming them. So this first one is 2-chloropropane. This one is 1-chloropropane. The difference just being whether the chlorine is on carbon 1 or 2. So there's a rule to tell us which one we get. Now, in truth, you get a little bit of each, but one is way favored over the other. And in fact, what happened, the one that's favored is actually this one. Now, it's not because it's symmetrical. The human brain really, really, really loves symmetry, so don't get tricked into thinking that chemistry or nature favors symmetry. In the case of chemistry, it does not necessarily favor symmetry. There's another rule at play here called Markovnikov's rule, named after a Russian guy. So Markovnikov's rule says when an unsymmetrical molecule of the form HQ, so Q is just a fill-in. That could be, in the two we've looked at, Q could be halogen or Q could be OH, hydroxide. The hydrogen atom from the thing being added becomes attached to the carbon that was in the double bond. So the only options are the two that were in the double bond, and it's the one that already has the most hydrogens attached. Now, there's a little saying that I like to add on this that it maybe is a little silly, but I think it helps you remember which way it goes. And it's always, remember, the rich get richer. The one that already has the most hydrogens up here, so if we look here, this carbon here has 2 hydrogens. This one only has 1. So as the rich get richer, the one that has 2 hydrogens already is the one that gets the new hydrogen, giving us 1 carbon with 3 hydrogens, and this one still only has 1. Doesn't get any new hydrogens. So Markovnikov's rule says in an unsymmetrical addition, where you can get 2 different products, where you have an unsymmetrical alkene, the one that has the carbon that has the most hydrogens already attached gets the new hydrogen. So, in compounds with more than 1 carbon bond, or carbon-carbon double bond, dienes, trienes, not to be confused with alkynes, but dienes and trienes, additions occur at each of the double bonds. So, I can have, if I have something like this, then I have to react with 2 molecules of hydrogen, and I just hydrogenate both. Oops, didn't do that right, did I? Didn't really do that right at all. Oh well, color scheme aside, you just add hydrogens to both. Okay, so as I said, the main thing you'll be expected to do is to predict products from these sorts of reactions. So hope that helped clear some things up, and I'll see you in class on Monday. I shouldn't be adding any more this weekend. I don't know why I'm adding this, because who knows when you're watching this. So see you in class.